Do you remember where we started talking about Newton, right? And Newton had this one famous observation. I can't remember what it was though. Oh, that's right. It was a falling apple. We can do it right now. Boom. All right, that apple is falling, right? Why? Well, Isaac Newton and you realize it's gravity. The force of gravity is all around us, and we just are used to living with it, right? On Earth, it always accelerates things at 9.8 meters per second squared. That means that every single second something falls, it gets 9.8 meters per second faster. In this lesson, we're going to solve some basic problems with gravitation and this acceleration. Let's take a look. First, let's consider our lesson objectives. We'll start by showing that gravitational acceleration is independent of mass. That means mass doesn't matter, which is kind of a surprising result. Then we'll practice solving kinematic problems with gravity. That's it, just 2 lesson objectives for this one. In the late 1500s, the Italian scientist Galileo is said to have completed an important experiment with gravity. We are told that he dropped 2 different objects of different masses from this famous Leaning Tower of Pisa. To everyone's surprise, they fell at the exact same rate, despite the fact that they had different mass. That's not what we expect. We expect instead something like this. Here's a drop test. We're dropping a feather and a bowling ball. And when we drop a feather and a bowling ball, we know that the feather will drop slower than the bowling ball. No surprise there. So in air, the feather drops more slowly. But here's the trick. If we remove the air and we drop them again, they actually tie. It's only the presence of air that makes them fall at different rates. Without air, it's a tie. This tells us something really important about gravity. The acceleration due to gravity does not change based on mass. So even though the feather is light and the bowling ball is heavy, they fall at the exact same rate. They're accelerated by gravity at exactly 9.8 meters per second squared. So we have a special symbol for gravitational acceleration, that little g there. Notice that this is just on Earth, and really specifically the surface of Earth. If you went up into outer space around Earth, it would actually get less strong. If you went to the moon, it would be totally different entirely. Now, this is also in a direction. Remember that acceleration has a direction. It's going to be down towards the Earth's surface. What we're going to do now is review our kinematic equations. Here's all 5 of them. And every time we spot acceleration, so that's in equations 3, 4, and 5, we're going to create new equations for kinematic problems with gravity. What that basically means is we're going to substitute those A's with G's. So now I've gone ahead and put G's in instead of those A's. What other change has been made? Did you notice it? It's the minus sign. We've changed the sign in front of the G to minus because gravity is accelerating downward. So I want you to have these equations handy when we go to solve problems with gravity. Here are the steps we're going to follow. We've seen these before. We're going to sketch the problem and identify our directions. We'll identify any knowns and our unknowns. What are we looking for? We'll convert if we need to. Then we'll find the relevant equations. We'll plug in our knowns and solve for our unknowns. And lastly, we'll think if our answer makes sense. Let's take a look at these problems. Let's put our gravitational equations to work. This problem says that a bowling ball with a mass of 12 kilograms is dropped from the Leaning Tower of Pisa, which is 57 meters tall. How long will it take to land on the ground? Ignore air resistance. Okay, that's good. We can ignore air resistance. Well, we're going to follow the same basic steps we did for our other kinematic problems. We're going to draw a picture, identify our knowns, review our equations, plug in our variables, and then at the end, make sure our answer makes sense. So let's start by drawing a picture. Here we'll draw the Leaning Tower of Pisa. And your picture does not need to be super pretty. Mine's not super pretty, let's be honest. We just need to get an idea of what's going on here. The height we know is 57 meters. And we're taking a bowling ball and we're dropping it off. Now, one key decision we have to make is where do we want to represent 0 height? So we could represent 0 height at the bottom of the tower, That would be totally fine. Or at the top of the tower. That's also totally fine. We're going to put 0 right here. So this is going to represent 0. All right, so that represents 0. And that means that our displacement final is going to be 57 meters below that, or minus 57 meters. Now, if you wanted to make the displacement final be 0 and the displacement initial be 57 meters, that would also be totally fine. You'd get the same answer. All right, let's think about what other things we know. Well, we know the initial displacement. We've defined that as 0. And then we also know the initial velocity. That's going to be 0. We know the gravitational acceleration. It's always on Earth 9.8 meters per second squared. And what we're looking for is how long it will take. In other words, time. So now we go and we review our equations for one that has displacement final, displacement initial, velocity initial, gravity, and time. Just one equation has all of those, and it's displacement final equals displacement initial plus velocity initial times time minus 1/2 gt squared. So that's the equation we want to use. Right away, some of that just drops out for us. That displacement initial is 0. That velocity is 0, and so when we multiply by time, that whole term will go away as well. So that makes our life a lot easier. We get displacement final equals negative 1/2 gt squared. Cool. Well, we want to go ahead and get t by itself. That's what we're solving for. And right now there's a fraction there. Nobody likes fractions. Let's get rid of that by multiplying by our denominator, which is 2. So we're going to multiply by 2. And actually, we'll bring along the negative sign there too. So we'll multiply by negative 2, and that'll get rid of our negative sign. So the fraction goes away, and the negative 2 goes away on the right-hand side, and we get negative 2 displacement final equals gt squared. Now we're going to move the g over to continue to isolate t. So we'll divide both sides by g, and the g will drop out. All right, let's continue our algebra. We're going to have now negative 2 displacement final over g equals t squared. The last step here is to take the square root of both sides. So we take the square root of the left and of the right, and when we take the square root of the right, square root of t squared just gives us t, so we'll erase that and just put a t. Now we're ready to go ahead and plug in all of our variables. Notice there's a negative sign under that square root, and that looks a little uncomfortable because we don't typically take the square root of a negative number. But luckily, we'll have negative 2, and we'll multiply that by negative 57. So when we multiply those two negative signs, they're going to end up going away, and we'll divide that by 9.8, which is the gravitational acceleration. When we plug all of that in, we'll get 3.41. And because our displacement, 57, has 2 sig figs, and our gravitational acceleration has 2 sig figs, we're going to round that to just 3.4. So we can drop that 1 in that case. Get out of here 1. And then we need to add units. Well, we're going to have seconds. That's the unit for time floating around here. So it's going to take 3.4 seconds to drop from the top of the Leaning Tower of Pisa. The next problem we're going to look at is super similar. So I want you to remember this answer, 3.4 seconds. I also want you to remember that the bowling ball has a mass listed there, 12 kilograms, that we never used. We could have listed it in our knowns, but mass just doesn't show up in our kinematic equations because it turns out not to matter. So when we look at the next problem, we're actually not even going to have to do any math. Let's take a look. It's going to be about our other famous object being dropped from the Leaning Tower of Pisa. This problem tells us that a feather with a mass of 0.15 kilograms is dropped from the Leaning Tower of Pisa, which is 57 meters tall. How long will it take to land on the ground? Again, we're going to ignore air resistance. Now, you could repeat all the steps we just did, or you could just remember that we never saw mass at all. So the mass just doesn't matter. When we're ignoring air resistance, these two will take the exact same amount of time to fall. And so that means that we know the time is equal to 3.4 seconds. Whether it's a feather, a bowling ball, doesn't matter. Now, of course, if we included air resistance, these would not drop at the same rate. But because we're ignoring it, it doesn't matter whether it's a feather or a bowling ball. Let's go ahead and take a look at the next problem, which will also involve gravity. This one says that a person is standing on the edge of a high cliff, and they throw a rock straight up with an initial velocity of 13 meters per second. What is the position of the rock after 3 seconds? And this is a problem from the T's physics textbook. Well, we're going to start by drawing a picture. So here is a nice cliff, and here is our person, and they're throwing a rock with an initial velocity that's up. and we know that the velocity initial is equal to 13 meters per second. Again, we need to decide what we're going to define as 0. And we'll be consistent here and just go ahead and take the top of the hill to be 0. So that's going to be our initial displacement. It'll be 0. And what we want to know is after 3 seconds, where will it be? So let's now go ahead and list our knowns and unknowns. Well, we already have listed our velocity initial, and we also know that our initial displacement is 0. What we want to know is its final displacement. That's what we're asked for. And we're also told the time. We know that it takes 3 seconds to get from wherever it starts to the position that it'll eventually be at. The whole time being accelerated by gravity, 9.8 meters per second squared, of course, in the downward direction. So we're throwing it up, and gravity is going to slow it down and then maybe pull it down. So it's not clear if our displacement final will be positive, that is, it hasn't dropped back down below the cliff, or negative, that would be it's dropped back down below the person. Let's find out. Well, once again here, you'll notice that all the variables floating around suggest the same equation we've already used. Namely, displacement final equals displacement initial plus velocity initial times time minus 1/2 g t squared. That looks like a q. Get out of here, q. gt squared. Okay, so we already know that the displacement 0 is 0, so it's going to drop out. So that's nice. And then we're solving for displacement final. So fortunately, in this case, we don't have to do any algebra. We just need to go ahead and plug in the velocity initial, which we know is 13, times the time, which we know is 3, minus 1/2 times our gravitational acceleration, which is 9.8, times our time squared, which is 3. So we're going to do 13 times 3, minus 1/2, 9.8 times 3 squared. Notice, if this term ends up being bigger, we're going to get a negative number, which means it will have dropped below the cliff. On the other hand, if this first term is bigger, we will know that actually it's going to be above the cliff. So what do we get? Well, when we plug that in our calculator, we do 13 times 3, we get 26. And then we subtract from that 1/2 times 9.8 times 3 squared, which is 9. You'll get negative 5.1 meters. And I've already rounded that to 2 sig figs. So since it's negative, that means our rock will actually end up below where the person started. So it's now falling somewhere about 5 meters below where the person was. So that's the displacement. Okay, keep this picture in mind. Let's go ahead and look at our last problem. This problem concerns our same person standing on the edge of a high cliff, and they still throw that rock up straight in the air with an initial velocity of 13 meters per second. What is the velocity of the rock after 3 seconds? Okay, this is your turn. Pause the video, try to do this entire problem, and then come back and we'll work it step by step. Okay, hopefully you did okay. Let's start with a picture. Same situation, we have our person on the edge of the cliff throwing that rock up with a velocity of 13 meters per second. And from our last problem, we actually know that eventually that rock will be below the person, traveling downward. So here we see for the first time that when we're going in the upward direction, our velocity is positive, and in the downward direction, we're thinking about that velocity being negative. So let's list what we know and solve for that final velocity. The initial velocity is 13 meters per second, and that's in the upward direction. So we're calling that positive 13 meters per second. Now you don't need to actually put the plus sign because anytime you write a number, it's assumed to be positive, but it is important to realize that's going in the upward direction. We know the time. We want to know what's going on 3 seconds later, and we know the gravitational acceleration, as always, is 9.8 meters per second squared. So we go and we look for an equation that's going to give us velocity final, because that's what we're asked for. So the correct one here is velocity final equals velocity initial minus gt. No, oh my goodness, gravity, you're not q. Ridiculous, you're g. So velocity final then is equal to 13 meters per second minus 9.8 times our 3 seconds. When we do that, we should get minus 16.4. Notice that our 13 has 2 sig figs and our 3.0 has 2 sig figs. So we're going to round this to 2 sig figs. And that 4 there means we'll round down, and so we'll get minus 16. What are the units? Well, our velocity that went in is meters per second, so our velocity that comes out will be meters per second. So that's the final velocity. Does that make sense? Well, yeah, because it's a downward velocity. So we know we threw the rock up in the air. At some point, it came to a stop, turned back around, and fell, and it's falling downwards at 16 meters per second. What have we learned? Well, we've showed that gravitational acceleration is independent of mass. That is, no matter how much stuff is there, it falls at the same rate. Then we've practiced solving kinematic equations with gravity, where we saw that we can substitute that little g and a minus sign in for acceleration for all our kinematic equations. Hey!